In today's lecture, I'll talk to you about the mechanics of river avulsions on deltas and their deposits. And we all know that variability is really a hallmark of sedimentologic and geomorphologic systems at a wide range of space and time scales. And I'll argue to you that quantifying the impact of variability might more often than not spring surprises on us and give us fundamental insights into the mechanics of surface processes and their deposits. So I'll convince you about this by focusing in on one example where we gained new insights into delta morphology, dynamics, and stratigraphy by quantifying the impact of flood discharge variability that typify natural fluviodeltaic systems. But before I begin, I'd like to acknowledge my collaborators who contributed to this work, in particular the people whom I've highlighted in bold here, and I'm also grateful to the funding sources that supported this work, with much of the funding coming from NSF, the Thor program at Caltech, and NSET 2. So like many things in fluvial geomorphology, this problem of the impact of flood variability on fluvial systems is something that Luna Leopold thought a lot about and made one of his many pioneering contributions, which is his idea of the bank-fill discharge and its relation to the hydraulic geometry. And this bank-fill discharge is really the discharge that fills an alluvial river, self-formed alluvial river up to its brim. And here I have a definition from the book of Tom Dunn and Luna Leopold, where they note that the bank-fill stage corresponds to the discharge at which the channel maintenance is the most effective, that is, the discharge at which moving sediment, forming or removing bars, forming or changing bends and meanders, and generally doing work, results in the average morphologic characteristics of the channels. And Luna, together with colleagues Wallman and Miller, came up with this idea of geomorphic work, where if you were to look at the rate of sediment movement as a function of bed shear stress and combine it with the frequency of floods also as a function of bed shear stress, the product of these two quantities is going to give us the geomorphic work, which is this dashed line that peaks at this bank-fill discharge, which corresponds to a discharge of roughly 1 to 2 year return period flood events. So what this suggests is that modest flow regimes transport the greatest amount of sediment over long geologic timescales. And this implies that we can take this probability density function of the flood discharges and collapse all this variability into this characteristic bank-fill discharge, and that's going to give us all the information that we need about the average morphologic characteristics of the channels. And as you can imagine, this has been a very powerful and influential concept that has formed the basis for some of the great work that has been done over the last few decades. For example, we run our physical experiments under constant discharge conditions, which is supposed to reflect this bank-fill discharge conditions. Most numerical models of topographic evolution and stratigraphic models either implicitly or explicitly make this assumption of the bank-fill discharge. And this idea also permeates into paleohydraulic reconstruction, where we assume that the deposits that we look at are reflecting the hydraulics of this characteristic bank-fill discharge. But over the last 5 to 10 years, there has been a growing recognition of the role of variability in geomorphology and sedimentology. In fact, Doug Gerolmack gave the first sharp lecture with the title "Noise is the New Signal." And here I'm going to highlight some examples across a broad range of space and time scales. So at short space and time scales, we are beginning to understand how the variability in the migration rates of bed forms resulting from suspended sediment is going to affect the shape of the bed forms and the bed form flux, and how these kinematics map into the stratigraphic record. The non-local theories of geomorphic transport on hill slopes and in rivers are built upon this hypothesis that sediment transport distances and sediment waiting times can be heavy-tailed, that is, they can be highly variable. And on really long space and time scales, we are beginning to understand how multi-scale variability in deposition and erosion can affect the rates of landscape evolution that we measure. So this is what is called as the Sadler effect, that is the negative power law dependence of the sediment accumulation rate as a function of the averaging time. And I think I've been really lucky to have been exposed to some of this work during my PhD. But what about river deltas? Should we expect that flood discharge variability affects deltaic evolution in a significant way? Now, this concept of bankful discharge is based upon this assumption of normal flow, that is, steady and uniform flow. And this approximation holds really well for rivers away from the coast, which is where Luna did most of his work. So under this assumption, the water surface and the bed surface are going to be parallel to each other, and the bed shear stress is a product of the flow depth and the channel bed slope. And river floods in these cases are accommodated by larger stage heights with little changes in the channel bed slope itself. Moreover, under this assumption, deposition at the river mouths is only forced by delta progradation, subsidence, and changes in sediment supply. But when rivers meet their shoreline, the normal flow approximation breaks down, and backwater and drawdown effects take control. And this is something that Jeff Nitrower and Mike Lamb talked about in their sharp lectures. So consider the schematic of a long profile of an alluvial river draining into a standing body of water, which is this constant sea level I've showed here. Now, because the water surface is pinned to the sea level, during low flows, that is the left-hand side of this PDF, the sea level is going to force the water surface to be concave up, which is going to result in the divergence of the water surface and the bed surface profiles, which in turn is going to result in flow deceleration through a portion of the alluvial river referred to as the backwater reach. So the length scale of this backwater reach can be approximated as the flow depth divided by the bed slope. Another way to think about the backwater zone is that it's roughly the length scale over which the riverbed topography is below the mean sea level. Now, in contrast to low flows, during high flows, that is the tails of this PDF, the sea level is going to force the water surface elevation profile to be convex up, which is going to result in the convergence of the water surface and the bed surface profiles, which in turn is going to result in flow acceleration through a portion of the backwater reach referred to as the region of river drawdown. So these non-uniform flows can extend several hundreds of kilometers upstream of the shoreline. For example, on the Mississippi River, the backwater length is about 500 kilometers. Importantly, within the backwater reach, the bed surface and the water surface are not parallel to each other, and variable flows are accommodated by changing water surface slope with little changes in the water stage height itself. And these hydrodynamics significantly affect the patterns of erosion and deposition within the backwater reach. For example, during these low flows, because of the flow deceleration, what's going to happen is there's going to be a wave of deposition that migrates downstream. So here in the schematic, positive is deposition, negative is erosion. And in contrast to the low flows, during high flows, because of the flow acceleration, there's going to be a wave of incision that initiates near the shoreline and migrates upstream. So we can right away see that the flood variability controls the patterns of erosion and deposition within the backwater reach, and this is where deltas are formed. So the central question I'm going to try and answer in today's lecture is, how does flood variability affect deltaic evolution and its deposits? And I have structured my presentation around answering three questions. First is, does variability in flows affect avulsion frequency? Does variability in flows affect avulsion location? And does variability in flows affect the architecture of the sedimentary record? And I'm going to answer these three questions using a combination of theory, physical experiments, and field observations. And I can tell you right away that the answer to all these three questions is a yes. So let's get into the first one of, does variability in flows affect avulsion frequency? So what are river avulsions? Consider the schematic of an alluvial river draining into a standing body of water. Now, as the river enters the ocean, it loses its momentum, its sediment transport capacity, it deposits sediment, building land through a network of distributaries, and creating what is called as a deltaic lobe. Now, once this deltaic lobe reaches a characteristic size, the river abruptly jumps to a new location and builds another lobe, and it does this over and over again in a cyclic manner. And this abrupt channel jumping is referred to as river avulsions, and it is through these river avulsions that many river deltas derive their fan shape morphology from. So river avulsions, which are characterized by this channel jumping rather than the gradual channel migration, are the primary mechanism by which many river deltas grow and redistribute sediment and water across the deltaic plain. And Doug once told me that he likes to think of these as earthquakes of the deltas, and this analogy works really, really well because like earthquakes, avulsions occur regularly and are catastrophic events that are dangerous to the communities living on deltas worldwide. And from the schematic, you can see that the river avulsions determine the fundamental length scale of the deltas. So here are some natural examples of avulsions on deltas. This picture on the left here shows deltaic lobes on the Mississippi through the Holocene, where avulsions are thought to occur every 1,000 years once, and the delta length scale is about 300 kilometers. In contrast, avulsions on the Wong He or the Yellow River Delta occur on a decadal time scale, and the delta length scale is about 50 kilometers. So how do these river avulsions occur? The process of avulsions has two fundamental requirements. The first is that at some location along the river channel, the riverbed aggrades over tens to hundreds and thousands of years until it becomes super elevated around its surrounding floodplain. And this is what is referred to as the avulsion setup. That is this riverbed aggradation that makes the channel unstable and poised for an avulsion. And the second requirement for an avulsion is a trigger, which is typically a short time scale flood event that results in the water flow to leave the channel, which in turn results in overbank flooding, a levee breach, and the relocation of the channel. And previous workers have argued that the process of avulsion setup is likely more important than the trigger because the channel has to be poised for an avulsion for a trigger event to cause the relocation of the channel. And this leads us to the river avulsion timescale theory. The river avulsion timescale, which is the average time between two successive avulsions, which is indicated by this TMA here, is thought to scale as the channel filling timescale TC, which is the average time it takes for the riverbed to aggregate by a characteristic flow depth. So HC here is the characteristic flow depth, and nu A is the net aggregation rate. Now, comparison of the measured avulsion timescale here on the y-axis with the channel filling timescale on the x-axis across lab and field data suggests that there's pretty good correlation between these two quantities. And here is the 1:1 line, and that's a 1:10 line. But what you would notice here is that there's a lot of scatter in the field data. So what we wanted to know was, is there a systematic trend within the field data that we look at there? So which leads me to the question of, does variability in flows matter in setting this avulsion frequency? And variability in floods should result in changes in the frequency and magnitude of overbank flows, which are thought to play a role in setting both avulsion location and timing. And so to test this hypothesis, we're going to look at this dimensionless avulsion timescale, that is this TA star, which is defined as the ratio of the measured avulsion time to the channel filling time. So we are removing the dependence of the avulsion setup here. So our hypothesis is that if you want to look at this TA star as a function of coefficient of variation of stage height, that is standard deviation by the mean, and that's a proxy for flood discharge variability. So if variability does not matter, we should expect that TA star should not vary with changing flood discharge variability, whereas if variability matters, we should expect some sort of a downward trend where avulsions happen faster than expected by the channel filling theory. And there's a reason to expect this because if you have more variable flows, the amount of channel filling needed for an avulsion to happen might be lower. So to test this hypothesis, we conducted experiments. And the reason for conducting experiments is twofold. One, avulsions occur really slowly in natural systems, and two, it's difficult to isolate variables in the field. So we conducted experiments in the River Ocean facility at the Caltech Earth Surface Dynamics Laboratory. The experimental setup consisted of the 7-meter long, 7-centimeter wide alluvial river that drained into the 6-meter by 3-meter ocean basin. So sediment and water were fed in at this upstream end, and the sea level was held constant to a sub-millimeter precision using a programmable standpipe at the end of this ocean basin. There were 6 cameras mounted which captured the deltaic evolution at a resolution of 1 minute, and an instrument cart moved up and down the system collecting data of bed elevation evolution and water surface evolution. And we conducted 2 experiments. First is what we call as the constant discharge experiment, where we held the sediment and water discharge to be constant, and we let the alluvial river build its own delta over 65 hours. And in contrast, in the second experiment, we oscillated between a 40-minute low flow and a 15-minute high flow over and over again for 160 times, and this is what we call as the variable discharge delta. So although neither of these experiments were scaled to any natural system, we can cast the variability in our second experiment in light of natural variability on deltas. So if you were to treat this 40-minute low flow as a bankful discharge on the Mississippi, this 15-minute high flow is going to be like a 20 to 30-year return period flood event. Importantly, an experiment was conducted under subcritical flows, and this is achieved by using crushed walnut shells as a sediment. And this works because crushed walnut shells have a density of 1300 kilogram per meter cube, that is, they are half as heavy as sand. So by using that, we could have low slopes and low flows, which resulted in sediment transport and deltaic evolution. And in our second experiment, for the variable discharge experiment, we held the sediment and water discharge to be in balance. That is, the sediment supply was equal to the sediment transport capacity for both the flows, such that the river bed slopes for both high and low flow were equal. So here is a movie of the multiple discharge experiment put together from time-lapse photography. So the 7-meter long river actually goes all the way on the left here. I've chopped it off. And 1 second in this video time is 1 hour in real time. And you can see there's a lot of action happening. I'm just going to annotate the video in a couple of seconds. So what you're looking at here is the dashed line was the shoreline. The river was entering a 10 centimeter deep water, which was our ocean basin. And then you can see the active channel here, which avulses to a new location, and that's the avulsion site. And we observed 41 such avulsions in our variable discharge experiment. So what I'm going to show you now is the bed elevation data at the avulsion site through time. So here is the bed elevation with respect to the sea level. So 0 is sea level here, and the x-axis is time after previous avulsion. So 0 is an avulsion, 600 minutes is another avulsion. And what you're looking at here is the channel bed elevation, that is the channel bottom. So you can see that there's a zigzag pattern resulting from deposition and erosion from low and high flows, which is superimposed on this long-term trend of aggradation. And if you look at levees, levees also build up during this time, but the difference here is that levees build up during high flows when you have overbank deposition. And this aggradation trend goes on until an avulsion happens, and there is the channel cross-section at the time of avulsion. So the gray profile is just before an avulsion, and the black profile is just after an avulsion, where you can see that avulsion happened by a levee breach. So now I'm going to plot the same data in a different space, where I'm going to look at this normalized channel filling, which is this amount of channel filling that happened with respect to the characteristic flow depth. So the y-axis here is this normalized channel filling, and the x-axis is the same, which is time since previous avulsion. So you can see that this normalized channel filling increases until it reaches a value of 0.5, where an avulsion is triggered and this value is reset and the cycle repeats itself. So we can see for this avulsion cycle that the critical channel filling was about 0.5 times the characteristic flow depth. And this value was variable over these 41 avulsions that I talked about, and we found that the mean was about 0.3 and the standard deviation was about 0.13. So now we have enough data to test our hypothesis, which was we're going to look at this dimensionless avulsion timescale TA star. We know TMA from measured the photographs that we have, and we know TC from channel bed elevation, and incidentally that scales with this characteristic channel filling needed for an avulsion to happen. And just to remind you, if variability does not matter, we should expect data to plot along this line, and if variability does matter, data should plot along the downward line. So what we see is that for the constant discharge experiment shown here, the TA star value is about 0.8, suggesting that the channel filling theory is actually predicting the avulsion timescale pretty well. Whereas for the variable discharge experiment, the TA star value is about 0.3, suggesting that avulsions were happening faster than expected by the channel filling theory. But these are just two experimental data points. What bearing does this have on the field? So to test if this trend holds up, we compiled a whole bunch of data on flood discharge variability, on natural fans and deltas, and here is how they plot. So you can see that this downward trend actually holds up pretty well, suggesting that avulsions may happen faster than expected by the channel filling theory in stormier environments. And we think that experimental data is offset from the field data because of lack of vegetated banks and sediment cohesion. So to summarize this section then, I asked the question of does variability in flows affect avulsion frequency, and what I showed you is that the channel filling at the avulsion site is really the prerequisite for setting up the avulsion. And flood discharge variability may play a key secondary role in setting the avulsion frequency. So moving on to the next section, which is does variability in flows affect avulsion location? So what I showed you before is that you need focused in-channel filling at a given site for an avulsion to happen. Now changes in water surface slope result in focused in-channel filling at a given site. If you have a decrease in water surface slope, that's going to result in a decrease in sediment transport capacity, which in turn is going to result in focused in-channel filling. Now on most systems like alluvial fans or fan deltas, this change in water surface slope is tied to a change in channel bed slope or a change in confinement, like shown here in this picture where avulsions are happening at the canyon fan transition. So we can think of them as being topographically pinned or upstream controlled, where the avulsion node is going to be spatially fixed and topographically pinned, and the fan can grow in time without impedance. Now, on many river deltas, avulsions also occur at a persistent spatial node, but without any apparent change in channel bed slope or in confinement. Now instead, field evidence suggests that on many low gradient deltas, avulsions occur at a characteristic distance upstream of the shoreline, which scales with the backwater length. So here the y-axis is the measured avulsion length, which is the stream-wise distance of the avulsion node to the shoreline, and the x-axis is the calculated backwater length. And this dashed line is the 1:1 line, and the shaded region are bounds of 2:1 and 1:2. So what this field data suggests is that they give us empirical evidence that avulsions on these deltas are occurring within the upstream portion of the backwater reach, that is between the 1:1 line and the 1:2 line. And it has been suggested using numerical models that this should be a result of variable flood discharges that result in persistent backwater hydrodynamics. But if this is true, it has really important implications for deltaic evolution. Because what this means is that the change in water surface slope is not topographically controlled, but is instead imposed by a downstream boundary condition of the sea level, and given consistent supply of sediment and water from upstream, your backwater length is going to be a constant, such that shoreline progradation should result in the downstream translation of the avulsion nodes. And again, I like to highlight here that it's really the variable flood discharges which result in this persistent backwater hydrodynamics, and it is thought that most coastal rivers are actually in a state of perpetual disequilibrium because the time scale of adjustment to large floods is longer than the recurrence interval of the floods itself. So this leads me to my hypothesis that if you were to look at avulsion length as a function of time for deltas, the delta is going to grow bigger and bigger until it reaches a size where the distance of the shoreline to the avulsion node is everywhere greater than the backwater length. Then beyond that time, the avulsion site should translate downstream with shoreline progradation such that the avulsion length remains to be a constant and it scales with the backwater length. And this is in contrast to the bed slope mediated avulsions that I talked about, which where the avulsions are going to be spatially fixed and topographically pinned, and the fan can grow in time without impedance. So we're going to test this hypothesis with the same experiments that I showed you, that is the constant discharge and the variable discharge experiments. And the key difference here is that in the constant discharge experiments, the flow tends towards normal flow, whereas in the variable discharge experiment, we design the experiment such that we have persistent backwater hydrodynamics. That is, the riverbed is always in disequilibrium with either of the flows within the backwater reach. Before I show you the movies of the constant discharge and the variable discharge experiment, I'm going to convince you that you're getting the backwater hydrodynamics right. So what you're looking at here is water surface and bed surface profiles. And the second panel is water velocity. The third panel is deposition and erosion. And all of them are plotted as a function of distance upstream from the shoreline. So 0 is the shoreline. Anything to the left is upstream. So what you see here is during low flow, that is this blue curves, we have this M1 curve, that is this concave up profile, which results in flow deceleration and sediment deposition within the backwater reach. The backwater reach is highlighted here by the shaded gray area. In contrast, during the high flows, we have this M2 curve, which results in flow acceleration and sediment erosion within the backwater reach. And these patterns of erosion and deposition are actually quite similar to those observed in the field. Here is similar data for the lowermost 500 kilometers of the Mississippi, which is the backwater length of the Mississippi. So here the blue curve is the base flow, the green curve is the bankful discharge, and the red curve is the 30-year return period flood event. So you can see that during the low flow, the water surface slope is small, which results in flow deceleration. And during high flows, you have a steeper water surface slope, which results in flow acceleration through the backwater reach. So these patterns of erosion and deposition resulting from flood variability are similar across lab and field data, despite the difference in 5 orders of magnitude in length scales here. So now I'm going to show you the movie of the constant discharge experiment. So this is the experiment where we held the sediment and water discharge to be constant, and we let the delta evolve over 65 hours. So 1 second in video time here is 1 hour in real time. So this is really sped up. What you'll see is that avulsions here are occurring at this change in confinement, and the river just sweeps back and forth, creating these really nice smooth shorelines. So even as the delta is becoming bigger and filling this container, the avulsion sites still remain fixed to this location, which is the change in confinement. So here is a movie of the variable discharge experiments, which I partially showed you in the beginning. So this is the case where we oscillated between the low and high flow over and over again for 160 times. And 1 second in video time again is 1 hour in real time. So one of the first things that will strike you is that the channel migration is restricted in this case. And we think this is because of the fact that the alternate bars created during low flow are destroyed during the high flow. And what you would see is that initially the avulsions are happening at this change in confinement, but as the delta is growing bigger, the avulsion sites are starting to move slightly downstream. So here you have avulsions occurring about at 50 centimeters downstream of this change in confinement. And you'll see that as this system evolves, you'll find more avulsions occurring around this region. So that's again still 50 centimeters. And you'll see an avulsion occurring somewhere up here now. So that's about a meter downstream of the change in confinement. So here are the avulsion locations overlain on the pictures of the deltas. And I have graded them from white to black, where white is early on in time and black is later on in time. So for the constant discharge experiment, you can see that the avulsion sites are tied to this change in confinement, and the delta just grows in time to fill the container. Now in contrast, in the variable discharge experiments, initially the avulsions are occurring at this change in confinement, but as the delta becomes bigger and bigger, these avulsion sites start to move downstream, with the latest set of avulsions happening about 1.2 meters downstream of this change in confinement. So now we can test our hypothesis. We can measure the avulsion length, that is the distance of the avulsion site to the shoreline, and we can see how it varies in time for both these experiments. So here is a hypothesis plot. The y-axis is the ratio of the avulsion length to the backwater length, and the x-axis is a dimensionless time, where I have normalized the experimental runtime by the time it would take to create a radially symmetric delta of half the backwater length. And that's essentially to account for the different amount of sediment discharges in both these experiments. So here is how the constant discharge data plot. So the avulsion length keeps on increasing in time, which is reflecting of the fact that the avulsion location is fixed and the delta was growing bigger and bigger. And I have actually chopped this data off. They actually go on to a dimensionless time of 4 and a backwater length of about 1.5. And here is how the variable discharge data plot. So initially the avulsion length increases in time until the delta reaches a size of about half the backwater length, which is a dimensionless time of 1. And beyond that, the avulsion sites migrate downstream in step with shoreline progradation, such that the size of the deltaic lobes remains a constant. So how is it that flood variability, which is the only thing we added to the system that is different, setting the avulsion location? So numerical modeling suggests that variable flood discharges will lead to a peak in in-channel filling in the upstream portion of the backwater reach. So just to remind you here, so the low flows, that is the M1 curves, are going to result in a wave of deposition that migrates downstream, whereas the high flows are going to result in a wave of incision that migrates upstream. And the hypothesis then is that this transient M1 flow deposition and the M2 flow erosion is going to result in a peak in channel filling within the backwater reach. So the y-axis here is a normalized channel filling, which is the amount of channel filling with respect to the characteristic flow depth. And this is the same quantity I was looking at when I was showing you the avulsion time plots, just that now I'm looking at in a spatial coordinates. And the x-axis here is the distance upstream of the shoreline normalized by the backwater length. So 0 is the shoreline, again anything to the left is upstream. And the hypothesis is that there's going to be a hump in this channel filling such that there's a maximum setup at some location within the backwater zone. So to test this hypothesis, we looked at detailed data through one avulsion cycle, that is from when a channel is formed to when it avulses again. And we kept track of this in-channel filling during each flow and also during a whole avulsion cycle. So here is how the low flow data plot. So the downstream translating wave of deposition peaks at about 0.35 times the backwater length from the shoreline, and the shaded gray area is the zone of progradation during this avulsion cycle. So we did not make any vertical measurements in that area. And this shaded blue area is the standard error from multiple low flow events during this avulsion cycle. And in contrast, during the high flow, what we see is that the upstream migrating wave of incision peaks at about 0.25 times the backwater length from the shoreline. And the cumulative effect of adding up these low flow and high flow events leads to this cumulative channel filling within the avulsion cycle that roughly peaks at 0.45 times the backwater length from the shoreline. And the avulsion cycle that I was showing you right now is at this green point here, where avulsion happens at about 0.45 times the backwater length. And the location of the avulsion very nicely matches up with the hump in this channel filling, which is a peak in channel filling at that location that results in the maximum setup for an avulsion to occur. And I'm only showing here data for one avulsion cycle, but this holds up for all those avulsions where the avulsion length was roughly a constant. So what this suggests is that it's really the variable river floods that produce this persistent morphodynamic adjustment within the backwater zone that lead to a peak in channel filling that scales with the backwater length. And it's not just the avulsion locations, but the flood variability actually changes the whole character of the delta. You can see here that these are shorelines graded in time, where you can see that the constant discharge delta has smooth shorelines, whereas the variable discharge delta has rugose shorelines. And this is because of the combination of this downstream translation of avulsion sites together with restricted lateral migration that results in these lobes forming. And there's something that Austin talked about on Monday. So what this suggests is that the short time scale flood variability may significantly affect deltaic evolution over long geologic time scales. So to summarize this section then, I showed you experimental data which suggests that avulsions occur at a characteristic distance upstream of the shoreline that scales with the backwater length, and it's really the flood discharge variability through persistent backwater hydrodynamics that lead to the emergence of this preferred avulsion node. But how about field data? Are they consistent with this hypothesis? So to test this hypothesis, the only place where you can really test this is the Wong-Her delta, which has the second highest sediment load, which in turn results in aggradation rates of several centimeters per year and renders the whole system unstable. So during the last 5,000 years, the river has shifted its course by at least 26 times, and there are two distinct avulsion nodes on the Wong-Her. One which is 700 kilometers upstream of the shoreline, which is the location where the river exits the lowest plateau, and the other which is 70 kilometers upstream of the modern shoreline near the city of Ligen. And we're going to look at what are the controls on the avulsion locations at these two sites. So first, the upstream node, where 10 major avulsions have happened in the last 5,000 years. So we extracted the long profile of the lower Wong-Her, And what we find is that the avulsion sites indicated by this red star here on both these plots is coincident with a tenfold change in channel bed slope. So these gray points here are local slope calculations, whereas these red boxes are window average slopes. So you can see that this location is associated with a tenfold change in channel bed slope. And theoretically, this decrease in channel bed slope might result in 50-fold decrease in sediment transport capacity, which in turn results in focused in channel filling. So this is the bed slope mediated river avulsion site. So the second location where avulsions are happening is near the city of Ligen, and you can see that there is no change in channel bed slope there. So is this probably a backwater mediated avulsion site? So to test this, so here is a plot of historical river avulsions on the Yellow River, and to reorient you here, the city of Ligen is right here. And we computed the backwater length using modern flow depths and modern channel bed slopes, and we find that the backwater length is about 20 to 50 kilometers, which suggests that this computed backwater length is consistent with the location of river avulsions. But that's not enough, because we have this new hypothesis which says that the avulsion sites should migrate downstream with shoreline progradation. So to test that hypothesis, we chose a fixed reference frame, which is the city of Ligen, and we measured the shoreline distance at 1855 and 1955. And here I should note that we're only looking at avulsions before 1936, because after 1936, avulsions were engineered on the system. So here you can see that the shoreline has prograded on an average about 0.12 kilometers per year, and that's the error from the radial averaging there. And we also measured the stream-wise distance of the avulsion nodes from city of Ligen, and they're plotted on the same plot here as these red points. And the data is noisy here, but statistically the rate of downstream translation of the avulsion sites seems to be consistent with the shoreline progradation rates. And importantly, the backwater length seems to be capturing these locations of avulsions reasonably well. So what this suggests is that despite this 12 kilometers of shoreline progradation, maybe the avulsion sites are in step with shoreline progradation such that the delta lobe size remains to be a constant. So to summarize then, I asked the question of does variability in flows affect avulsion location, and what I showed you is both experimental and field data which suggest that avulsions on deltas may occur at a characteristic distance upstream from the shoreline that scales with the backwater length. And through experiments, I showed you it's really the flood discharge variability through persistent backwater hydrodynamics that leads to the emergence of this preferred avulsion node which scales with the backwater length. So in the last section, I'm going to talk about how this variability in flows might affect the architecture of the sedimentary record. So one of the implications of our work is that flood variability can result in erosion near the shoreline, and these incisional features can result in erosional boundaries in the rock record which may appear similar to those previously interpreted in terms of allogenic changes, such as changes in sediment supply or relative sea level fall. And we identified two autogenically generated sources of incision. The first is what I call the flood-induced scars. That is the floods which result in this M2 flows, which result in this wave of incision that migrates upstream. And here is experimental data highlighting that point. The y-axis is elevation above sea level, x-axis is distance upstream of the shoreline, normalized by the backwater length. And what you're looking at here is the dashed black line is the bed profile at the beginning of the high flow, and the solid black line is the bed profile at the end of the high flow. So you have incision only within the backwater reach here. And it's also been shown in the field by Jeff Nitrower, where he showed that the Mississippi River near its coastline is a mixed alluvial bedrock system. So this depth of the scar can be scaled as roughly to be equal to the difference between the normal flow depth of the high flow and the low flow. And using a compilation of modern discharge data, we think this might be roughly between 1 to 3 times the characteristic flow depth. So the second sources of autogenically generated erosional surfaces are avulsions. Avulsions can drive cut and fill cycles because of the river shortening that results in the steepening of the river. And that will result in a wave of erosion that migrates upstream. And the depth scale of these scars are going to be equal to the critical channel filling that is required for an avulsion to happen. And that we saw that using experimental and field data that it scales roughly with the channel flow depth, but the minimum is roughly 0.2 to 0.3 times the channel flow depth. So now that we have the depth scales, what are the length scales over which these erosional scars propagate? So following previous work, we modeled these waves of erosion as a diffusional process where the diffusivity is dependent on the unit sediment flux and the river slope. And what we find is that the flood-induced scars have a length scale of about 1 backwater length, and they originate at the shoreline and migrate upstream. And here is the same experimental data highlighting that effect. And the avulsion-induced scars also seem to scale with this backwater length, that is, they migrate by 1 backwater length during an avulsion timescale. But the key difference between the two erosional scars is that this one originates near the shoreline, whereas this one originates at the avulsion node. So together, we can expect these autogenically generated scars to span about 1 to 2 times the backwater length from the shoreline. So I'm going to show you these two effects in the experiments. So we built synthetic stratigraphy from our experiment using the elevation time series. So this red line is the elevation time series, and we identified the erosional surfaces as the lowest elevation such that no future elevation is lower than that given value. So if that is the elevation time series, that is a stratigraphic recording. And we're going to look at the synthetic stratigraphy at this location where the river exits the narrow section in our experimental facility. So here is how the synthetic stratigraphy looks at this location, where the erosional surfaces here are graded in time from green to black, where green is stratigraphically oldest and black is stratigraphically youngest. And you can see you have these stacked channel deposits within a deeper valley system, and we know that these stacked channel deposits were formed by erosion and deposition during low and high flow, and this deeper erosional boundary was formed because of an avulsion. So now let's test the hypothesis of the depth scales and length scales of these scars. So we're going to look at the scar depth normalized by the characteristic flow depth, and the x-axis is the distance upstream of the shoreline normalized by the backwater length. And here is the flood-induced scars, and the maximum value here matches up with what we expect from our theory is about 0.35 times the characteristic flow depth, which incidentally happens to be the difference between the normal flow depths of a low and high flow, and that's maximum near the shoreline, and it decreases as you move upstream. And the error bars here are from multiple avulsion cycles. So I'm averaging over many avulsion cycles to show you these data. And the avulsion-induced scars also have a maximum at this avulsion site, and that value is about 0.4 times the characteristic flow depth, which roughly is what we saw in our experiment, is 0.3 times, but here it's 0.4 times, and that decreases as you go upstream. So to summarize then, what we should expect from autogenically generated erosional scars is that you're going to have a maximum somewhere near the coastline, and that's going to decrease as you move away from the shoreline, and it's going to become minimum somewhere between 1 to 1.5 times the backwater length. So to test this hypothesis in the field, we did fieldwork at the late Cretaceous fluvio-deltaic stratigraphy in the Castlegate sandstone. And one of the main reasons we went here is that many people have already been to this field site, and it's a well-studied field site. In fact, Van Wagner, in his 1995 paper, lays some of the foundational principles of sequence stratigraphy by looking at these fluvio-deltaic stratigraphy. So deposits that we're looking at is the deposits of these deltas highlighted in the yellow box. One of the nice things about this system is that you have multiple fluvio-deltaic stratigraphic units. The Castlegate sandstone overlies the desert member, which is also a fluvio-deltaic unit. Another important aspect here is that previous work by Andy Petter has already recognized the effect or the signature of backwater effects here, where he found that the flow depth increases as you go downstream towards the shoreline. So here is a depositional model for the Castlegate rivers, where we found that upstream of the backwater zone, the deposits were highly amalgamated channel bodies with a lack of mud, which indicate the system was braided with high lateral migration. And we inferred the paleo-shoreline location by looking at wave ripple deposits and oyster buildups. And what we find is that these multi-story channel bodies and incised channels are only limited to the backwater zone of these paleo rivers. So now we can look at the data by knowing from our experiments what to expect for autogenically generated erosional scars. So here is the measured scour depth as a function of the distance upstream of the inferred shoreline. And this is a combination of our own data with data from existing literature. And here these gray points are raw data, and these red boxes are binned averages. So you can see that this maximum scar depth is at the shoreline, and that decreases as you go away from the shoreline, and it roughly reaches a minimum value at one backwater length. And if you were to compare this cover depth as a function of flow depth, what we see is that both the Castlegate and the experimental data fall within this range of expected from zone of autogenics. And this lower bound here is the avulsion limit, that is 0.2 times the flow depth, and the upper bound is the flood-induced limit, that is from the modern compilation of flood discharge data. So what this suggests is that the field observations are consistent with our theoretical expectations and experimental insights of erosional scars resulting from floods and avulsions. So to summarize then, I asked this question of does variability in flows affect the architecture of sedimentary record, and what I showed you is that during high floods, rivers can be erosional near their shoreline, which can leave erosional boundaries in the rock record. And floods and avulsions can result in autogenically generated erosional boundaries within the backwater reach and maybe a little bit further upstream. So I have two conclusion slides. First, I'm just going to recap the main results of what I showed you today. First is that the flood discharge variability plays a key secondary role in setting avulsion frequency by reducing the critical channel filling needed for an avulsion. And I showed you this by this downward trend of this TA star value with an increasing coefficient of variation of stage height. And flood discharge variability through persistent backwater hydrodynamics sets the preferential location where avulsions happen on deltas, and we saw that this backwater mediated avulsion sites can migrate downstream with shoreline progradation. And finally, floods and avulsions can leave erosional boundaries in fluvio-deltaic stratigraphy without any external changes in the boundary conditions. So I motivated this talk by citing these examples of how variability is important across these broad range of space and time scales. And what I showed you that deltas actually fit pretty well into the spectrum where short time scale variability may significantly affect deltaic evolution and its deposits over long time scales. And I think there are exciting opportunities for us to quantify the impact of variability in sedimentologic and geomorphologic systems, and maybe more often than not, it can spring surprises on us and give us fundamental insights into the mechanics of surface processes and their deposits. Thank you very much.
I'm sure many of you have questions.
Go ahead.
Yes, thank you for your presentation, and I like your experiments. They were very compelling. I have a
Thanks.
question. I'm wondering, you changed the flow discharge, the durable experiment. Did you change the sediment discharge to maintain a constant sediment concentration?
Yes, so sediment supply rate was equal to a sediment transport.
Could you repeat the
Oh, sorry. The question was that did we change the sediment discharge at the same time when we changed the water discharge in our variable discharge experiments? And the answer is yes, the sediment supply rate was equal to the sediment transport capacity for each of those flows, such that the river bed slope never changed in the normal flow reach of the rivers.
Thank you.
Gordon.
That was a great talk. I wonder whether you thought about other fluvial settings where the backwater doesn't play such a prominent role. And I'm wondering whether the variability that you speak to would be as strong. It seems that the backwater effect and the fact that you get this sort of mechanistic switching sort of a fundamental driver of the phenomena you're describing. I'm just wondering if you thought about other pieces of the system where that backwater effect is not playing such a role.
So the question was, have I thought about other systems where the backwater effects may not be playing such an important role? And the answer is no. And I think the reason why it works here really well is because the patterns, the fact that the coastal rivers may be in a state of perpetual disequilibrium allows for this variability to manifest itself in long-term dynamics. So the really key thing to look for, I think, in other fluvial systems might be that what is the time scale of response to, say, floods, and how often are they occurring. So if they don't occur often enough, then the system is just going to aggrade itself to that given, to an equilibrium, and then the variability won't matter. Yep.
So, are there places in this work that you expected variability to matter and you found that it didn't?
So the question was, are there examples in this?
Just
No.
broadly speaking, places where you were
Yeah.
variability could matter, should
Yeah.
expected it to matter, and it surprised you that it didn't.
So I think the null hypothesis should be that variability is only going to give you a degree of detail around the mean field behavior, but in some cases it can spring surprises. But I think what is important is to keep an eye out for it. It's not necessary that, so in this case, that like the bed forms, variability resulting from migration rates from suspended sediment is going to change the shape of the bed form significantly. But if you're interested in migration rates, maybe that's not so important. But there is a degree of, it's how detailed do you want to go into the problem matters. Bill.
The variability that you examined is equivalent to a flow variability.
Yeah.
What would be the effect of tidal variability, which can be quite substantial in some ways?
Yeah. So tidal variability, one thing, so the question was, I looked at flow variability and how about tidal variability. And I think tides will definitely play a really important role in filling abandoned channels and thus affecting reoccupation of whole channels and the whole dynamics of the system. So I was only interested here in avulsions, and we thought that tides, the time scale of tides and the morphodynamic adjustment that they cause may not be important on avulsion time scales, but that's just true for some systems. Maybe it plays a role somewhere else that I haven't looked at yet. Doug.
This maybe is more of a technical question, but I'm interested. You had an example from the morphology in your experiments where when you had a constant discharge, you had a smooth radial delta.
Yeah.
And when you varied the discharge, it was more rugose.
Yeah.
And other experiments, like ones that we've done, when we used just a mixture of sediment, we got very rough shorelines for a constant discharge. And so
Yeah.
I'm wondering if you could speak to, I know that wasn't the focus here, but whether that morphologic expression is maybe, is there something specific about discharge, or if there's just disorder? Disorder at a local scale can create sort of large scale
Yeah.
rugosity, and if you could speak more to that, or your thinking on that.
So the question was that Doug's experiments on fan deltas, he had rugose shorelines resulting from sediment mixtures, right? And there's a lot of great work on this, like Hoyal and Sheets and Kyle Straub recently, and Doug Edmonds, of course. And so there are many of these things which point to rugose shorelines resulting from sediment cohesion. I'm not ruling that out. All I'm saying is there's an additional mechanism which can also result in rugose shorelines.
Yeah, no, I was saying perhaps there's something more general that just some kind of disorder, any kind of disorder shakes the system into sort of large-scale rugose shorelines. I hadn't seen that similarity until your experiment. Your variable discharge ones look just like the ones where people use sediment mixtures in a constant discharge. That's fascinating.
Yeah, that's interesting. Fido.
So I saw you talk about 4 or 5 other experiments that it shows like the
So the question was, why is it that our lab data and the Mississippi data look so similar? And I think it's because we got the hydrodynamics right. That's a short answer. Oh, right. So that's the adverse slope that you're referring to, where it enters the shoreline, and then you have this depositional bump, right? The scour resulting in higher velocities? I think I didn't understand the question, sorry.
It's because of the bifurcations that precipitate also.
Oh, right, so yeah. Cool.
Yeah,
Alex.
How variable does the variability have to be for you to actually notice these cuts? I mean, you gave one example. If you made it a bit variable or a lot variable, how different would it be?
So the question was, how variable does the variability have to be to see this effect? So we deliberately chose two discharges, one from the M1 regime and one from the M2 regime, such that we can see the interplay between the backwater and the drawdown effects on delta evolution. And it's the same. So we are trying to represent the whole right side of the PDF of discharges by one peak. So instead of having the whole discharge and having one representative discharge, we're having two representative discharges of the whole PDF. So did I answer your question?
Yeah, in essence, but if you had much wider flow variability, even if you boil that down to some larger areas with that, would you see something different?
So the patterns of erosion and deposition for all the M1 flows and all the M2 flows are going to be similar, just that the magnitude is going to change. So I think that the answer for this question is not going to be that much different, even if we ran a whole PDF of discharges over and over again. Yeah.
Well, let's give Vamsi a hand for a really exceptional talk. So that concludes the Sharp lecture and our program. I hope to see you all at the reception. And John has a box of T-shirts for those who are interested. Thank you very much.